Well, thank you for coming to my presentation. Today, I will be presenting about my PhD project that I finished back in 2019, and it's about the Watershed tungsten deposit, and it's located in Northeast Queensland. So today, I will be, well, the title kind of says more or less what I would like to show you as an outcome. Like we have a couple of mineralization events, but I want to demonstrate with vein textures and microprobe analysis, geochemistry, and some other techniques that we have a Permian upgrade after a Carboniferous magmatic hydrothermal mineralization event. So this project was part of a bigger project that was funded by the GSQ and also involved the industry, the GSQ itself, and several postdoc and PhD students from JCU. So tungsten, it's a very it's an element that has a very high melting point in excess of 3,000 degrees Celsius, and also a very high density, like similar to gold, about like 18 grams per centimeter cubic. So it is used in a lot of technological things that require a lot of high temperature things, like for example, airplane flaps or turbine blades, drilling tips as well, and as well as some darts and the defrost of your window in the back of your car. So this is a picture of scheelite. One of the interesting things is that it shines blue under UV light. That's if it's like pure scheelite or pure tungsten rich. Then if scheelite has a bit of moly, then this color will be a bit yellow. That if it has a bit greater than 10% of moly, it will be yellow. But and then I will be showing that Watershed only has some only tungsten-rich scheelite. This is a map that shows the distribution of tungsten deposits around the world. As you can see, most of the deposits around the world corresponds to vein stonework or skarn. Usually the vein stonework ones are associated with grayson alteration, associated with intrusive bodies. The skarn deposits are very, you can see that in Asia, especially in China, they are very common, especially because in China there's plenty of carbonate rocks, so a lot of calcium as well to generate these tungsten-rich skarns as well. So today we are going to zoom in into Northeast Queensland there, where we have a thin tungsten province. And well, before that, I'm showing this graph where you can see that the main producer of tungsten is China, very close to what is producing in the entire world. Then we see here Australia, that was kind of steady in growing from 2001, but then 2016, one of the producers was Mount Carbine in North Queensland that they stopped producing, so that's why we have this shift. And then also, if we consider the amount of tungsten that we have at Watershed, which is about 55,000 tons of tungsten, we see that it's roughly the amount of tungsten that China produces in a year. So if Watershed enters into production, which is not a deposit at the moment, that's more or less where Australia can go up in tungsten production for 10 years. So this is the location of Watershed. Watershed is located about 100 kilometers to the northwest from Cairns. This is the resource at the moment. This number varies because now I'm showing it in tungsten trioxide, but it's one of the largest undeveloped tungsten deposits outside of China. The deposit is now owned by Tungsten Mining, which purchased from Vital Metals in 2018. And this watershed was discovered in 1978 after Utah Development Mining. They ran a regional stream sediments and they found stream sediments anomalies in excess of 200 ppm on 1 kilometer strike. So after that, they developed the resource until the mid-80s, where tungsten price dropped until Vital Metals, they purchased the deposit in 2005 from BHP at that time. And they developed this resource, which they got to this number back in 2014. And since then, it's been in care and maintenance. So tungsten system. So what's the motivation of this project? As I told you before, this was part of the bigger GSQ project for Queensland as a way to promote exploration in the area. And one of the questions that we have specifically for Watershed and as well as Mount Carbine, that was one of the other projects that was working in this GSQ project, was that Mount Carbine, for example, and Watershed as well is hosted just in sheeted veins. And then we see that in China, most of the deposits are very close to intrusive bodies associated with grays and big skarns. And so then when we compare the style of mineralization that we have in Northeast Queensland, it's very similar to what they see in China in the higher levels. So basically, you go from these narrow veins on top to kind of wider veins at depth. And then when you get close to the intrusive body, you have skarn generation or brazen alteration with very big tungsten deposits. So for example, here in Queensland, we have a resource and production of 0.17 million tons of tungsten trioxide historically. And one particular deposit in China, the Dahutang, has 1.1 million tons of tungsten trioxide. So the main question is, do we have that intrusive body at depth or not? So that's was the main question of this work. And that's what I will show you and see where is the tungsten coming from for Watershed specifically. So this slide shows here on the right a map of Northeast Queensland. So a bit of geological context here. We are in the Mossman orogen here in blue. The Mossman orogen comprises deep marine sediments that they are Silurian to Devonian in age. And this Mossman orogen metasedimentary rocks are cut by S-type granites in this area and more I and A-type granites around the southwest over there. So we have few tin and tungsten deposits. So the main tungsten dominant deposits that we have in the area are Mount Carbine and Watershed over here in yellow, and then we have some smaller deposits over here, which comprises also Wolfram Camp, that it's a Grayson tungsten deposit in a cupola of the intrusive. And then also we have some small tin deposits. So the Collingwood cluster over there of tin deposits, the Herberton area, and the Kangaroo Hill. And also here it's the it's the only area where we can see the equivalence of the intrusive bodies here, that they are the Kennedy Igneous Province. We see here some volcanic volcanic rocks associated as well as to the Kennedy Igneous Province. Oh yeah, so what I want to show here is some ages. So the ages for the deposits over here, they range in the south between 345 to 340 more or less. And then you see that progressively they get younger towards the north. I will be showing more detailed ages about Watershed later, but you can see that there is a predominant younging age from south to north. This other map is a zoom in into the Hodgkinson province, which is the northern area of the Mossman orogeny over there. So over here we see that we have a part of tungsten deposits around Watershed. We have the Hodgkinson gold fields as well, which are interpreted to be a orogenic gold system. There are a lot of papers about this from Vladimir Lisitsyn from GSQ. The historical production of all this gold in this area is roughly a bit greater than 1 million ounces. So it's not much of a significant at the moment. So yeah, so Watershed is surrounded by these S-type granites. So you can see here in light blue, it's called the Waipala supersuite. They're mostly S-type. Watershed is surrounded by these S-type granite. So you tend to think that most likely the deposit is, the origin of the deposit is from these intrusives. But we will be showing some things that this is a bit of a discrepancy between the intrusive and the orogenic situation there. So yeah, zooming into Watershed specifically. So what we can see here on the map is that Watershed is located in the Hodgkinson province, Hodgkinson formation. Here the gray color corresponds to slate and slate breccias, which some authors, they call it melange, which is the main rock type around the area. So we also have these samite pots, and also here in green, there is a bit of skarn altered conglomerates. So this has it has a very it's very deformed, and then the main orientation of the sedimentary package, well, it's towards the northwest. So most of the mineralization is associated to veins. Most of the veins are mostly east-west, and they dip slightly to the south, very steeply to the south, and also associated with some shear zones that they are mostly north-northwest oriented. And also we can see that some of the dating of the intrusive bodies that they are cut in this sequence, they are mostly Permian. So a dioritic body over here and a couple of granitic dikes that were dated at 275 more or less. So next slide. So these are the rock types that I just explained. So the rocks are very deformed. It's not very easy to get a stratigraphic column. So these are the main rock types that you can find at Watershed. So the main one is these slate breccias, where you can see some shales, basically shales with some pots of samite in it, and quartzite, where the quartz grains greater than 2 millimeters, the samite, and then this conglomerate, which is usually altered to skarn, where you can see that they have like a reddish color associated to garnet. This darker color corresponds mostly to clinozoicite, which is an iron poor epidote. So this is how the intrusive rocks look like. So this is a monsonitic dike. So as you can see here, this is the rock, and this is under the UV light. So these monsonitic dikes, they are very high grade. They have probably up to 20–25% scheelite. However, this is not volumetrically very important. And this is only found in drill hole. So then we have all these other intrusive rocks that I already talked about. This Kubaba granite is associated with the big S-type granites that they surround Watershed. And you can see that the texture is way different compared to the intrusive or dikes or granitic dikes and dioritic dikes that they occur within the deposit. So, okay. So if you see the ages, we see that this it's a 350 million years old dike, and all the rest are Permian. These are Carboniferous. So this is an example of how the host rock look like. We have like with this we can deduce some of the deformational events. So we were able to describe or to define at least 4 deformation stages, where D1 and D2, you can see that it's a very upright isoclinal folding with transposition, and we separate them. We define 2 events, but very likely maybe there are more than 2. But just for simplification, we define 2 events here. And then we have a D3 event, which corresponds to mostly open folds that are with a bit of granulation. And then these D1 to D3, they are mostly ductile deformation. And then we have a D4 that is mostly associated with shear zones in brittle ductile environment. So the D4 is the event that is associated with the veins and the mineralization as well. So this is a long section along the deposit. So over here we can see a little map. This is from A to B. We can see here the samite in light blue, the slate and slate breccia in gray, and then in green we see the skarn altered conglomerates at spots there encapsulated usually in samite. So what we can see here is that the quartz veins that host the mineralization, they are preferentially developed in skarn altered conglomerate in green. So that's a very important observation, because you can see that the deformation and the conglomerates, they behave in a more brittle in a way compared to the slate that it's more ductile. So it's more easily to open and for the fluids to trespass these conglomerates. And as well, you can see here that most of the mineralization is associated to all the veining. Similarly, here in this is a cross section from C to D. Here we can see more that the rock is more deformed, that the folding is more tight, because we are cutting across the deformation basically. And also we can see here the same thing, that most of the veins are developed in the skarn altered conglomerates. Oh yeah. So yeah, same thing here. You can see that the tungsten grades up to more than 1% develop very well in the veins. And then here, that's the sample where we took for that dike. This is an example of an outcrop scale map where the star is in this map, where you can see that the veining here in red, they develop in different orientations, mostly associated with shear zones. The shear zones here in blue, you can see that are associated with quartz veining. Here in the host rock is skarn altered conglomerate, and then mineralization is mostly associated here in yellow in scheelite. It's mostly associated to areas where we're close to these shears. So, and then the other observation here is that most of the veins that are east-west, they are wider than the ones that they are oriented in north-south or north-northwest. So just by doing a paleostress analysis, we can see that most of the veins were formed in a east-west compression and a north-south extensional regime. So as I said, mineralization is mostly scheelite. The scheelite that we have here at Watershed is tungsten, is pure scheelite, is tungsten pure, not much moly over there. So that's why we see blue. Otherwise, we'll see it a bit yellowish. I have some samples here that we can check after with a beer or something. I have the UV light as well. So the bulk of the mineralization is in quartz splash veins. And also in vein halos, but also we have scheelite in skarn altered conglomerate and monzonite. And also this image over here shows a CL, cathodoluminescence image of a scheelite. So where we can see that scheelite, usually they have some core, some growth zones around that core. And in most of the cases also we have some resorption. So we have scheelite that continue growing through time through different deformational events. I will show more details about that later. So this is the paragenesis of Watershed. It's a bit crowded, but the main take point home thing here is where we have all the stages like D1, D2 to D4, the same that I already defined. But what we can see here in skarn altered conglomerate and veins is that we have a particular paragenesis that is very common for scheelite deposits. In the literature, if you go and check, we usually have scheelite associated with what they call the oxide event, which is usually predate a sulfide event here. So that's classic, and most of the time you will see those cross-cutting relationships if you encounter some tungsten deposits around. So here occurs the same. We have scheelite that occurs in monsonitic dikes. Here we have the dashed lines. Although I show you that it has a lot of scheelite, but it's not volumetrically important, so that's why the dashed line. And then also we have scheelite associated with retrograde stages associated with D4. So we have 4 retrograde stages. And then, well, I will show you more detail in the next slide. So we will start with the skarn altered conglomerate. So this is a snap of the skarn altered conglomerate paragenesis. So here, these images, they correspond to scheelite that precipitated during D1 and D2. So we can see here in the skarn altered conglomerate that the scheelite has like these hook shapes, most likely related to a dynamic crystallization of scheelite. And then these monsonitic dikes that they are flooded with scheelite. So we are kind of looking this D1, D2 event. Then in D4, what we have is this in vein, we have, these are the style of mineralization, the veins. So basically, as a first event, we have quartz with a bit of platch in the margins that then is subsequently cut by this retrograde stage 2 that contains most of the scheelite associated with albite and quartz over here in the margin. Then these veins open up, and you have like later events comprising quartz, comprising muscovite, chlorite, tourmaline, and fluorite. And then these dark areas here in the bottom left corresponds to pyrrhotite as well. So it's a late stage as well. Also, we have some veinlets cutting through the skarn-altered conglomerate, which are a bit different style of mineralization compared to the D1 that were deformed scheelite as well. And as you can see here in this image as well, we have massive scheelite crystals of about, this is 2 centimeters. So we have a bit of a nuggety effect. And this other texture corresponds to scheelite growing at 90 degrees from the wall, the vein wall, corresponding to tension veins. So these are some examples of shear-related veining textures. So this image here on the top left corresponds to platch, where you can see that the twinning is a bit deformed. It pinches a little bit. That's a sign that the vein was deformed or the platch formed during the formation, as well as we have this recrystallization around quartz margins as well. Then we have this other texture where we have like scheelite and quartz and platch growing in orthogonal to the strike of the vein. And as well as this image is a thin section, so this is more or less 5 centimeters or 3 centimeters along. But there we see that the scheelites along the veins are more elongated. So when we have like veins that are more northwest oriented or northeast oriented, we see this crystal growing parallel to the vein margin. And this image here to the bottom right, what it shows is like this quartz platch veins that they develop very well in samite or skarn-altered conglomerate, but then when they encounter slate, they pinch out. So that's a sign that very likely all this was mostly generated as stress efforts rather than probably an intrusive that you may encounter. If you have an intrusive body coming up, you may generate more stockwork or veins in all the rock types, not only selective in on some rocks. So this other image shows it's from the microprobe. It's a backscatter image. So where here we see a platch and scheelite. So this is a zoom in of the relationship between platch and scheelite. What we can see here is these red and blue dots, which are microprobe dots. And what we can see is that in the platch, that they are a bit farther away, not in contact with scheelite, they are more a bit calcic rich. And then when you have scheelite precipitating along the platch margins or co-precipitating, we have a shift on the composition. It's more albitic, more sodium rich. So that we can think that maybe tungsten was traveling or was moving as a sodium tungsten species. That's an important thing to understand in the deposit. Here, this other image, it shows a clinozoisite from D4 replacing garnet from D1 or D3. So the interesting thing here is that when you replace clinozoisite, when clinozoisite is replacing garnet, as we can see, clinozoicite has less calcium than a grossular or garnet, normal garnet. So we're liberating calcium that may help to generate scheelite as well. Yeah, so this is a summary. So just to wrap up the ages and the events. So here in this diagram that is from both 2007, we can see that the Hodgkinson Formation was deposited in the Silurian Devonian. Then we have some events. This corresponds to around the in Carboniferous corresponds to the monsonitic dikes. I have some few ages of uranium lead in titanite that also shows that a metamorphism was active between 320 to 250 included, so even Hunter Bowen orogeny. And then we have the granitic dikes about 270 to 281. These other ages, the yellow stars correspond to argon-argonine muscovite. So most likely, this one, most likely the age of the mineralization around 275. And this age corresponds to a cross-cutting muscovite central line that cuts through all the paragenesis. So we will go through some of rare earth elements in scheelite. So since scheelite has calcium, it can incorporate a lot of rare earth elements. So you can deduce some sort of origin for the scheelite. So here we can see the trace element, the rare earth element pattern for the different scheelites from different rock types. So you can see a bit messy, but here in the scheelite in monzonite, so you can see that most likely they are slightly enriching light elements, light rare earth elements, which is roughly the same rare earth pattern from the monzonite itself, and these ones correspond to scheelite that it's resorbed or has been altered after the formation. So also here in the veins, usually what you would expect from scheelite is to have like a perfectly flat pattern. However, here you see that you have a bit of an enrichment in the heavies as well. Yeah, so I will go to the next one, which is more important. So yeah, so based on the rare earth element patterns or rare earth data, what you can deduce the origin of the scheelite. So this scheelite is from the literature. So you can see here in this yellow contour is scheelite that occur together with orogenic deposits, orogenic gold systems. The green one corresponds to skarn mineralization, and the light blue that goes around this area corresponds to intrusive scheelite. So what we can see here is that most of the scheelite that from monsonitic dikes plot perfectly or roughly in the area where the intrusive scheelite from the literature. So also we have some outliers, but these outliers correspond to resorb or altered scheelite that was modified after it was formed. So to do this exercise is very critical to understand very well where your scheelite occurs or what's the texture as well. So also here in the blue, sorry, the red dots corresponds to the scheelite in vein that plots mostly in the orogenic load gold scheelite, which is this demonstrate that scheelite most likely was derived from metamorphic fluids. So also we can use scheelite as a redox proxy. So just by using the European normalized to chondrite and the European asterisk, it's basically what the European should be, considering samarium and GD. So what we can see here is that if your scheelite plots along this line, your scheelite was forming more oxidized conditions. It means that you have European 3+ in scheelite. If you plot a bit away from this line, like the scheelite from the veins, it means that your scheelite, it's more enriching European 2+. That shows that we have a bit of a shift from a bit oxidized condition to slightly more reduced conditions when we have when we form the scheelite in veins. Also here, the low moly content of the scheelite also reflects the reduced conditions, because usually moly is more mobile under moly 6+. So that's also demonstrate the reduced environment of the watershed deposit. Here also we can see these diagrams also shows that we have two types of scheelite, but it's mostly similar to the previous triangle that I showed you before. So just jumping into the isotopic data. So this is what we did. We took samples from scheelite and platch that coexist together in the vein margins, and we tried to calculate a temperature and also an origin for the fluids. So what we have, So what we have here is that this black squares corresponds to the hydrothermal fluid, or the water in equilibrium with platch and scheelite. So here we can calculate that scheelite was deposited around 300 degrees ±50. So it's a bit scattered, but it gives us an idea more or less on that we're around green schist phases environment. But using this, we cannot say if it was a magmatic or metamorphic fluid that formed this scheelite from veins. So we also analyze oxygen and hydrogen isotopic data from muscovite from retrograde 3. And we calculated several compositions for the water in equilibrium for this muscovite at different temperatures. Most likely, muscovite form around 280 or even less than that. But considering all the lowest temperature of formation for the muscovite, we see that plots are roughly at the metamorphic water origin for this muscovite. Also, the sulfur isotopes, they show that they have a high here around 0. So this usually is interpreted that we have a magmatic origin for the sulfides, but also another alternative is that if we see this diagram, this curve here corresponds to the sediments that host orogenic gold deposits in meta-sediments. And these are the sulfur isotopic data of the orogenic, of the sulfides in the orogenic deposits themselves. So this curve it's basically it's an historical curve, and we can see that the watershed host rock age of watershed plots very inside this curve. So another hypothesis is that the watershed was formed because of the reducing the sulfur of the host rock of in this case the Hodgkinson. So possibly this is showing that also the sulfur to form the sulfides has a metamorphic origin. And in terms of fluid inclusions in quartz and scheelite, what we have here is that after performing some Raman, we have methane, and also we found that we have some graphite. So that also shows that we're in a very reduced environment comparable to orogenic gold system, that also in those systems you have a bit of methane in those fluid inclusions. And this is the plot of the fluid inclusion assemblages. We see that the temperature that we got from the isotopic data fairly correlate with the age, no, sorry, with the temperatures that we got in fluid inclusions, and very low salinities, under 6, max 9 there. It's a classic fluid inclusion data from the tungsten deposits that they are scheelite rich. So now jumping into whole rock geochem. So the main idea here was to try to understand with this sampling technique from vein halo, and scan-altered conglomerate, we try to understand how the elements were brought into the system, which were brought by the veins, which were scavenged from the wall rock. And for that, we took 14 samples from vein and halo and 8 from scan-altered conglomerate. And then also we did some far field signals in sammites, mostly because we don't find scan-altered conglomerate or scan-altered rocks outside of the watershed. So yeah, again, so just to analyze this data more than say, oh, we have this amount of tungsten or this amount of tin. The main idea here was to understand how the elements are enriched or depleted in certain rock types. So what we did is, like, we took all the whole rock geochem and we applied a center log ratio. This is a technique just to open and to open the system, because basically when you get your geochem from the lab, it's a closed system, 1 to 100. With this technique, you kind of open up the system and you can compare better your data. And then by doing the set score of that, then you can understand how many standard deviation is your sample out from the what is happening as a baseline here in 0. So here this plot shows rare earth elements. So basically here you can see that this well, here in this area is vein samples. This is halo. This is scan-altered conglomerate, and these are sammite, more distal. So just focusing here around the red line, we can see that for rare earth elements and high field strength elements, we have that possibly these elements were leached from the halo into the veins. The veins, that you can see, is very scattered because of the nature of the vein is very negative. So, and the other interesting thing here is that in the rare earth elements, in the halo, we see that it's more enriching light rare earth elements, and in the vein it's more enriching heavy rare earth elements. So possibly it's telling us that we have that leaching of the halo into the vein. So here for the ore elements, we can see that most of the ore elements, considering beryllium, boron, scandium, copper, moly, rhenium, and tungsten, it's mostly enriched in the veins and very likely brought by the veins into the system. And same as same as the previous here, the skarn elements, mostly the calcium, all the calcilicate elements, including fluorine. As well, we have that possibly we leach them from the vein from the halo into the vein. And for the little elements as well, we have an enrichment in lithium, rubidium, and cesium in the halo. Very likely because we have a lot of mica in the halo as well. So just zooming into these ones, so what we can see is that the veins are more enriching in tungsten, rhenium, copper, scandium, boron, and beryllium. And they decrease going out into the halo and the skarn. So most likely moly and rheniums in scheelite, copper and scandium in apatite, scandium and beryllium in phlogopite, and copper in sulfites. And then we have these skarn elements that are leached from the host rock into the vein. So we are talking about that the skarn is enriching fluorine, phosphorus, and all the calcium, manganese, iron, strontium, and tin. So these are a bit depleted in the halo as well. So most likely they were scavenged by the vein and incorporated into the vein, considering that we have plage, that we have calcium and strontium, scheelite calcium, apatite, potassium and fluorine, and fluoride, phlogopite, and sulfite. So one of the interesting things here is that fluorine also enhances the rare earth mobility. So this is possibly what is happening here too, because we have a bit of fluorine in the vein and scavenging the rare earth elements as well into the vein. You need a bit of fluorine. Not much to say about this other one. We doing more the footprint of the deposit using the samite. With the variations are very subtle, but we still have a similar enrichment going into Watershed. So tungsten, moly, copper, rhenium, calcium, iron, manganese, lithium, and cesium. More likely they're enriched towards the deposit and a depletion of calcium and sodium and rare earths, possibly showing that the fluid was scavenging sodium to form the veins and so on, and the plage with strontium and barium. So yeah, just to conclude, we have several events. We have an early stage mineralization event at 350 that then what happened is that was the Hodgkinson was cut by these granitic dikes. Mineralization most likely occurred at 275 and it's Permian. And source of the fluid mostly metamorphic. Just that's based on the vein width, the formation of vein minerals, the methane in fluid inclusions, and the isotopic data. We have possibly two stages of scheelite, the magmatic, hydrothermal, and the one that is more metamorphic in origin in veins. And most likely scheelite is in equilibrium with sodium, so most likely was traveling as a sodium tungstate compound. And then the scheelite the scheelite in skarn associated with clinozoicite after garnet liberates calcium to form the scheelite. And also, and with this one I conclude, is the ternary rare earth element diagram differentiates very well the origin of the scheelite. The redox conditions of scheelite using the European anomalies shows that we shift from a relatively oxidized fluid to more a reduced fluid. So very likely this is because of the interaction of the fluid with all the reduced host rock. And then in terms of far field signals, we have that tungsten is mostly associated with beryllium, boron, scandium, copper, moly, and rhenium. And these fluids leach rare earth, neodymium, and all these skarn altered skarn elements. from the skarn-altered conglomerates. And in terms of regional footprints, it's very subtle, but we have a similar enrichment towards watershed compared to what I just said previously. So thank you very much.
Thank you, Hammy. Thank you, Hammy. Any questions from the floor? Come on, don't be shy. Here's one.
Thanks, Jaime. That was really interesting. Do you think there's a million tons of tungsten sitting in the ground underneath it, like the Chinese example you spoke of at the start of the presentation?
Well, it's hard to say with the data I have, and that's considering several factors, because as you can see, the geology is very dismembered. So in most of the cases where they use this is they use a lot, for example, the garnet composition going outside. So sometimes in some tungsten deposits, you can see associated with skarn, you can see that, for example, spessartine is more enriched going into the causative intrusion. The problem here is that the system is so dismembered and you have skarn-altered conglomerate inside the rock and pinch out, pinch in, pinch out. You cannot do that exercise to see, oh, we have that just using the garnet. In terms of vein width, it's a bit hard as well, because depending on the orientation of the vein that at watershed, for example, if they're east-west, they're wider. If they're more kind of at low angle to the shear zones, the veins tends to be a bit narrower. So you cannot kind of use directly, oh, vein width, let's go. If veins are wider, let's continue drilling. Although I think the deepest drill hole is 600 meters, so there is still room to see that. And I mean, I may be wrong. I hopefully be wrong. But one of the important things here as well is that monsonitic carboniferous dike, that maybe if they drill deeper, they may find that dike expands and you can find, I don't know, like 50% scheelite in that, like at depth and volumetrically important. So I think what I forgot to say as well is that for exploration takeaway, probably those monsonitic dikes, 350 million years old, those are probably the things that you want to chase there.
Thank you. There was a question over here. Yep.
Okay, yeah, great talk. Just one question. If you look at the variography of the mineralization for Watershed, there's a very strong along strike component at right angles to the cross-cutting veins. Have you got any explanation for that?
Sorry, can you repeat?
Sorry?
Can you repeat the question?
Oh, right. If you look at the variography for the mineralization at Watershed, there's a very strong along strike component at right angles to the quartz veins. Have you got any suggestion as to why that would be?
What do you mean with the variography?
If you look at the continuity of the mineral grade.
Oh, I think it's related to that. I think it's related to the host rock, because you have that the conglomerates where most of the veins are hosted. Those are the only rocks that kind of open up in a brittle fashion compared to the shales that are more ductile, and there is no much fluid penetrating into those rock types.
Yeah, no, well, this mineralization is all in the samite.
Yeah.
So presumably then there's porosity in the samite from the original phase of formation associated with the monzonite. You know, so you got your primary mineralization's gone through by the metamorphic fluids, possibly related to the monzonite, to form this disseminated scheelite in the samite, and then you've had your later veins, whatever your Permian time afterwards. Would that be a reasonable suggestion?
You mean like that that the monsonitic then after deformation liberated a bit of more tungsten? That's what you...
Well, there's what you said, there's a monzonite dike.
Yeah.
So there's not a widespread amount of monzonite.
No.
So that's a bit difficult then generating the metamorphic fluids from the monzonite to populate the porosity of the sandstone, samite? Or is the samite already prepared for porosity and the scheelite mineralization?
I think that, okay, so I think the samite, the samites are not mineralized. So it's mostly this conglomerates that they are skarn altered. So potentially over there was some sort of limestone layers that because of deformation, everything was metamorphosed and you have this skarn assemblage. So one of the important things here is to have the calcium availability as well, which I think that the skarn gives that as well, plus the space, plus the porosity, as you said, of the conglomerate. The samites are a bit quartz rich. It's not a good host.
But a lot of the mineralization is in the samite, is it not?
No, in skarn altered conglomerate.
Okay,
So
is that the
it's a bit-
samite? Is that the arenite breccia, the conglomerate? If they renamed it,
So what
because there's a lot of arenite breccia there.
the samite is the arenite, basically. It's like a sandstone.
Yeah.
Original sandstone, quartz, feldspar, muscovite. But yeah, it's not mineralized.
Sounds like a conversation over a beer.
We can talk later.
Any other questions from the floor? I think there's a couple from online. No, I'll bear with me while I run across here. There's a couple of questions from folks at home. Kevin asks, is the plage and orthite in the quartz and plage plus scheelite veins? Don't worry, I've answered my own question. Thanks, Kevin. Kevin asks, what is the garnet composition?
I have a slide there I can show afterwards. So yeah, that's the garnet composition. So the D1, D2 garnet composition is mostly, most of the garnets are grossular rich, calcium rich, but the metamorphic garnets are mostly almandine. It has more iron +2 and more manganese. And then the D3 garnets that kind of overgrown some core, or they have some growing zones here. They shift into more the grossularitic composition. So yeah, that's basically interpretation where we see like kind of these deformed Boudinage garnets. I interpreted them as metamorphic, but also they have some growth zones. That those are the ones I interpreted as more D3, more evolved.
Thank you. And Travis asks, any association with magnetite or siderite?
No, it's magnetite pool.
Magnetite pool.
Magnetite pool, yeah.
Okay. And to extend that a little bit, perhaps, is there any wolframite or other tungsten minerals, or is it purely scheelite?
It's purely scheelite. So further south, Mount Carbine, that one has wolframite.
Okay.
And wolframite is essentially you replace the calcium by the iron.
Okay.
So, and the thing is that further south at Mount Carbine, you have some metabasalts layers. So there also you have the iron to come in, compared to in Watershed that you have like this calcium-rich host rock that act as a trap for the mineralization or the fluids.
Thank you. Any other questions from the floor? No, it looks like we're all done. Thank you, Amy.
Thank you very much.